Hello everyone, my name is Eduardo Puerta, and I will be presenting the results of my and my collaborators' work on the effect of printing orientation on the reading experience of 3D printed Braille. To begin, I would like to establish that 3D printing is already used for making accessible interfaces, and as researchers and designers, we should care about the standards for making them usable. 3D printing has been used as a method to create graphics in education, as described by Buehler et al., orientation and mobility models, like the ones evaluated by Holloway et al., and even to label medicine. These can provide tools to bridge design gaps for people with visual impairments, who may not be at the center of the design of many everyday things. Fused deposition modeling is a type of 3D printing that has been praised for being comparatively inexpensive to other forms of Braille and tactile graphics production. This is the type of printer that we will be focusing on in this work. Tobias and Hertz highlight its community access in libraries and disability centers. And finally, 3D printing provides customization, which may be useful for designs intended for people with different visual conditions. However, for fused deposition modeling, the angle at which an object is printed impacts its surface quality and structure. Spoiler alert, this means that for the case of Braille, the angle of print can influence how smooth or sharp the Braille is to the touch after being printed. Now, I would like to clarify exactly what we mean by orientation and print angle. Let's say that we want to print a thin flat plate with Braille, say for a sign. Now, we have to choose if we want to print this plate, for example, horizontally, so that the plate lies on its back, fully horizontal with the Braille on top. We will call this horizontal Braille. Or conversely, we could print it standing up vertically on one of its sides, say the long side, with the Braille in the front, and we will refer to this as vertical Braille. The print angle, then, refers to any of the possible slants in between those two cases. We also note that the angle of print is not the same as the angle at which people read them. We print plates with removable supports and encase them so they all lie flat for participants to read however they are most familiar with. Now, to understand why there is a difference, fused deposition modeling creates objects by stacking layers of molten plastic. Because of this, the orientation influences where the steps of the layers lie in the Braille. Van Vieren et al. Describe the staircase effect and where the steps are and how they affect the smoothness of the surface. Among other things, as the printer moves back and forth, sometimes small plastic defects get left behind, and the angle of print impacts where these defects are in the model. Finally, whenever a higher layer is printed on the air, as opposed to over another layer, the object may warp. In fact, text is recommended to be printed horizontally, with the letters being on top of the plate to avoid this problem. Now, if you know this, it may seem counterintuitive that some prior work has established that printing vertical Braille is preferred to horizontal Braille, which is the opposite of text. A white paper from the Diagram Center presents this recommendation. Therefore, in this work, we expand upon their findings by conducting an empirical evaluation to determine the experience of people reading Braille printed at various angles. The main contributions of this work are the designs and results of these experiments for a more granular selection of angles. And similarly, we draw from the literature and our results to provide some recommendations for designers looking to incorporate Braille into their 3D printed interfaces. By 2 experiments, we designed an evaluation of sanded stimuli and of stimuli directly from the machine, which we call unsanded. Note that the main intention of this work is not to compare sanding as a condition, but in pilot testing, we found that some of the plates could be harmful when read as fast as possible. So sanding allows us to remove some of the larger defects, while having an unsanded experiment gives us a more straight-from-the-machine experience. We also note that sanding is a common form of post-processing 3D printed objects, specifically to remove some of the large defects that may hurt participants. We analyzed the data from 12 participants recruited via the Carroll Center for the Blind in Boston, Massachusetts. 10 participants identified themselves as being completely blind, 1 is almost completely blind with some light perception, and 1 as significantly low vision. We randomized angle-sentence combinations for the reading speed tests, pulling from an extended corpus of standardized sentences used to measure Braille reading speed. Participants read the sanded plates first in a randomized order, and we measured reading time by looking at the audio recording. In between plates, we asked participants to respond to a 7-level Likert questionnaire, asking how much they agreed the Braille was comfortable and readable. We did the same for the unsanded experiment, excluding reading speed. We also asked participants to provide comments in an open interview style. Finally, we incorporated a control which consisted of Braille embossed on stock paper by a traditional Braille printer. Let us examine some of the results from these experiments. We found our statistical analysis to determine that the reading time was significantly impacted by angle. I will highlight that the angles that participants read the fastest were 90 and 75 degrees on average, which were the vertical Braille and then the next closest one. This aligns with the results from the diagram center. Similarly, we also found a pattern consisting of angles 60 degrees, 75 degrees, and 90 degrees being more consistently read faster than their lower angle counterparts. However, I think the most interesting results are the participants' responses, so let us examine those. For the sanded experiments, we asked about both discernment and comfort. Overall, participants found all Braille to be discernible, with a dip in ratings for angle 15 and 30. The patterns for comfort are very similar, but some of the participants did feel neutral on average about the comfort of the Braille, for angles 30, 15, and 0. Finally, for the sanded experiment, we also see this pattern of 60, 75, and 90 degrees outperforming all other angles. Generally, we found participants describe some of the lower angles in negative ways. For example, participant 5 described how the plate with angle 30 was rough and prevented them from gliding their fingers. Similarly, participant 12 described the plate printed horizontally at angle 0 as horrible and claiming how the dots are taller but rough. For the unsanded experiments, we also collected Likert responses. First, we know how they show similar trends to the sanded experiments, but with more pronounced patterns. For discernment, participants still generally agree that the plates are discernible, with 15 and 30 being the only angles that fall below that threshold. For comfort, participants generally find higher angles to be more comfortable, with the steepest difference around 45 degrees. With that in mind, we also found that 75 and 90 degrees outperform lower angles, just like the other metrics. These patterns are also reflected in participant responses. We know how participant 0 described the vertical Braille as better than some of the sanded ones, and as pretty smooth overall. The plate 60 was described as good but jagged. The plate 30 was described as one of the roughest. And the horizontal Braille was described as unpleasant because of their roughness. From this, we gather that angle does significantly affect the reading experience across all metrics: speed, comfort, and discernment, for both of the experiments. We also find that there seems to be some tipping point at the 45-degree mark, where all angles above perform better than the angles below. Now, what does this mean for the signers? I think the biggest finding is that we found no discernibility, comfort, or performance difference between 75 and 90 degrees. And this means that designers have a more range of choices without sacrificing the experience of readers. especially as we described that printing at 90 degrees can be detrimental to other surfaces, like text being one of them. We also highlight the case of a participant, participant 1, who actually preferred the Braille printed at 75 degrees, mentioning that it was smooth and comfortable to read, but a little bit harder to discern, with the 75-degree plate as being described as the best one so far, and specifically commenting on the dot height being good, the space being good, and the texture being good as well. Now, we do want to highlight some limitations of this work, specifically the generalizability to long text. This is also something that came up with participants, with one of them mentioning that plate number 60 was not particularly uncomfortable, but it is not something that they would read for long extended periods of time. However, we still believe that this has applications in signage and the types of labels that would be used in small models. Now, our biggest recommendation is that Braille should be printed at angles above 45 degrees, but ideally as close to 90, with 75 being one of the recommendations we make. In the paper, we also highlight that identifying when adding Braille into a model is reasonable is an important aspect of designing, and we also highlight that post-processing like sending with a dual resender can be important. If you want to hear more about these, please read our paper. Thank you to all my co-authors, and thank you to all for the time. Have a good day.